Hello everyone and welcome to the 24 Hours of STEM. My name is Ella from Team 3132 and I will be your host on the Math Stream for the next 6 hours. Over the next 24 hours, people from around the world will present on interesting and thought-provoking topics associated with STEM and all FIRST Robotics programs. We want to be able to continue and share our appreciation for STEM, even in times of international hardships, so thank you for joining us today. Now, it is time to get into the presentations that will be featured across the two streams, Mass and Energy, for the next 24 hours. So just sit back, relax, and get ready to learn about STEM. It is my pleasure to introduce our first speaker, who will be talking to us about AI and machine learning in the FIRST Tech Challenge. So please join me in welcoming Tom Eng from FIRST. Hi.
Hey
Hi,
everybody,
Tom,
can you hear me okay?
Yep.
Okay, great. Sort of dark in my room, but that's okay. My name is Thomas, and we're going to be talking about artificial intelligence and machine learning in the FIRST Tech Challenge. And my background is a mechanical engineer, and I am the senior engineering manager at FIRST. And here's an agenda. Can you see my screen okay?
Yep, screen sharing is doing all good.
Okay, great. So today we're going to talk about artificial intelligence and machine learning. We'll just do a little general overview. Then we'll talk in specific about AI and ML within the FIRST Tech Challenge. Then I'd like to talk a little bit about training an inference model. And when I mentioned the phrase inference model, that's the model that's used by a machine learning system to recognize patterns and make decisions and make guesses based on the patterns that it detects. We'll talk a little bit about the tools that we use in the FIRST Tech Challenge to create these inference models. And then we'll end up with some fun activities that you can try on your own, which will give you some insight and some exposure to these machine learning and artificial intelligence technologies. So I'm not sure if, oh, and by the way, if you have questions, feel free to pose them through the, the question and answer mechanism for Zoom. And I might defer some of the questions till later, but I'll be happy to answer them. And the moderator can just, interject and raise the questions as they arise. But many of you probably have heard in the news, if you've been following it over the past few years, stories about artificial intelligence and machine learning. They're becoming more popular. And you might ask yourself, why is there such an interest in both of these topics? Well, even though these technologies are somewhat in an infancy, artificial intelligence and machine learning has matured, and people are doing or solving or trying to solve interesting problems using these technologies. And if you could put it in the context of today's days, with the COVID pandemic, you might have heard or read about some scientists who are using machine learning technologies to try and look for patterns to determine what kinds of policy decisions can be effective to reduce the spread of the COVID virus. And also they're looking at, for instance, drug candidates and methods to actually treat the virus, and using machine learning to try and see which would be potential candidates and more effective candidates to treat someone who's been exposed with COVID. And when we talk about AI and machine learning, when we talk about AI specifically, the term artificial intelligence is used to describe a machine or a device that mimics cognitive functions that are normally associated with a human or a human, or an advanced creature like, an animal, a dog or a cat or something like that. And so something like computer vision, we think of vision as in the past something that was distinctly, a higher order function of something like a intelligent creature, a human, animal, and so forth. But there are machines that can use cameras and can process images and recognize patterns and make decisions based on those images. And that, in essence, is an artificial intelligence type of this machine or device. Similarly with speech recognition, the ability to listen to sounds and distinguish specific words, spoken words, is something that formerly we would associate with a human function, but that can be done by a machine. And then more abstractly, problem solving and learning. These are things that can be done by machines, which are human-like, and therefore we consider them part of the artificial intelligence set of devices. When we talk about machine learning, it's similar, but it's a little different. In this sense, machine learning refers to the science of developing machines and algorithms that can perform tasks without explicit instructions. And instead, these machines can use patterns or pattern recognition and inference or guesses to perform these tasks. So if you think about it, if you were doing an artificial intelligence versus machine learning example, well, you can, for instance, build a robot that would navigate a maze very precisely. And you could tell it saying, hey, for this specific maze, I want you to drive this many centimeters. I want you to turn at this time or after these many centimeters have elapsed. And I want you to turn this many degrees in the clockwise direction and so forth. And using these prescriptive instructions, you can have that robot navigate very accurately through a specific maze. If you were going to develop a machine learning system that does the same task, instead of being prescriptive and having these explicit instructions for it to be successful, you might teach that robot how to recognize obstacles. And then you might teach that robot how to make informed decisions based on what it senses and what patterns it detects, so that it can navigate that maze or another maze independently. And so when we talk about machine learning tasks, these machine learning systems can complete certain tasks, even though they're not explicitly programmed to do so. And they do that, again, through pattern recognition and by making guesses, making informed guesses based on the patterns they observe. Okay, and machine learning is a subset of artificial intelligence, but not all examples of AI are also examples of machine learning. Okay. Any questions, or are we good so far?
No questions so far.
Okay, great. So let's talk about specifically an example related to technologies that are used within the First Tech Challenge. The First Tech Challenge uses, for example, something called Vuforia. And Vuforia is an artificial intelligence type of package, and it's actually a computer vision related package. And Vuforia can be used by First Tech Challenge teams to look for and track specific image targets. So on the left-hand side here, I have BB-8 in an image from a Star Wars movie. And this was one of the image targets that was used in this past First Tech Challenge season. And teams could use this, and if their robots saw this picture, they would precisely know, well, first of all, they'd recognize the picture using this Vuforia software, and they'd precisely know where they are with respect to that image. And that's, kind of cool. It's like the robot can do something that we formerly would associate with a human. It can, look for and detect and recognize and then localize off of this image that it's known to it. Well, if you look at a machine learning example, it's similar, but a little different. Teams can use a technology called TensorFlow from Google, and TensorFlow has the ability to recognize that there are dogs in all of these images. Unlike Vuforia, where the system is looking specifically for this image target, something that's been trained with an inference model can look at an image it's never seen before, such as these pictures of the dogs, and then based on the pattern that it detects, say, hey, I think there's a dog in each one of these 4 pictures. And I think, by the way, the dog is located here, or here, or here, or here. And that's what machine learning has the ability to do. It can solve these problems and complete these tasks without being programmed explicitly to do so. It doesn't have to look for a certain image. It can look for patterns and make guesses or inferences based on what it observes and say, hey, I'm 90% sure that there's a dog sitting right over here in this picture. Okay. So let's talk specifically about these technologies and the First Tech Challenge. The First Tech Challenge is sort of unique in the fact that we use an Android controller for our robot control system. And that gives us advantages because it is an Android controller. There are technologies such as Vuforia, such as TensorFlow, that can be run on an Android system. And in 2016, the First Tech Challenge introduced support for PTC's Vuforia augmented reality software. And we use that technology to allow our teams to look for these 2D image targets. And based on the position of the targets, when a robot sees and recognizes those targets, it can very accurately navigate autonomously on the field because of this Vuforia technology. And each season, when we release a new game, we also release two-dimensional navigation targets that are strategically placed along the perimeters of the field so that robots can use these targets to navigate autonomously. In 2018, First Tech Challenge introduced support for Google's TensorFlow machine learning software. And it's similar, but a little different. In machine learning technology, or the machine learning technology that we implement, we provide teams with the ability to use this TensorFlow technology to detect and track game elements in the field. So rather than saying looking for a specific image, they're taught, or the system is taught to recognize something like a ball or a cube or something unique that's a game element in the system, and then teams can then use TensorFlow to detect and track these objects during a match. Every season, First Tech Challenge, since we've introduced TensorFlow, creates a pre-trained inference model, and that model is designed to be able to detect certain elements of the current season's game. And so to date, that's how we've introduced teams to these technologies. And in some sense, we've kind of insulated them from the complexity of all of this technology and made it sort of like a sensor. You can use a pre-made function to check, is there any of these objects visible in my field of view? And if so, where are they visible within my field of view? And you don't have to know too much about machine learning or TensorFlow or Vuforia, and you can use it as you would a sensor. But if you're interested, there's more there underneath the covers, and as well as to support it with documentation if you wanted to learn more about how these machine learning or artificial intelligence technologies work. And moving forward in the First Tech Challenge, First would like to continue to explore fun and meaningful ways to incorporate AI and machine learning tasks into future challenges. So we want to make it fun. We don't want to put in this technology for technology's sake, but we're looking at ways, for instance, of maybe creating a challenge where teams have to, instead of using a pre-trained model, create their own inference model so that they can detect some kind of custom game element to score extra points. And again, our goal is to really expose kids to the 21st century tools, which will be relevant as they continue studying on in the future, and also start working in the the real world. And hopefully they'll have exposure and experience with these technologies and be able to do some interesting things in the future with these technologies. Specifics, PTC Vuforia, again, every season we put these image targets around the game field, and this is a representation of the image targets that were placed in this past season's game. And using these image targets and the Vuforia technology, a robot can very accurately determine its location on the field. Now, I know that there are other technologies such as odometry that are very popular and very quick to be used on the First Tech Challenge field to navigate autonomously and with high reliability and accuracy. But the vision system is still also a very good option. For instance, if you use odometry and your wheels slip, you might get an inaccurate measurement and might not accurately maneuver. If you use, for instance, Vuforia to check your position, you can find one of these image targets and verify your location on the field within a few centimeters accuracy, and have an alternate way to place yourself on the field using this computer vision technology. So that's pretty cool. And here's a demonstration of Vuforia, and what we have is a robot, and I don't know if you could see this video, but this robot is trained to detect this Vuforia image and then always maneuver so that it's about 9 inches away from the image and directly in front of it. And you can see that it's very responsive, the robot, and the whole point is that this Vuforia is really powerful stuff, but it does this at a very high frame rate. So it can detect and track these images with high degree of accuracy and do it like in 20 to 30 frames per second. Okay, so now I'm going to move on. Let's move on to our next slide. And let's talk about TensorFlow. So TensorFlow is, again, a complementary technology, and we talked about how each season first provides an inference model, and that inference model can be used to look for game elements on the field. On the left-hand side, we see an image from a robot during the Rover Ruckus season. And what it's doing here is it's looking for TensorFlow, or using TensorFlow for objects that it recognizes. And when it finds it, it's going to draw a bounding box around it and label it and tell the user, hey, I'm 96% certain that there's a gold cube here. And then it'll tell it where it thinks it is. I'm 66% certain that there's a white wiffle ball or a silver mineral here. And then it'll tell you where it thinks it is. And then it says, I'm 90% confident that there's an element here. And similarly for the next season, we did that for this past Skystone season, where we had an inference model that can detect these game elements. So it detects these yellow stones, which do not have the sticker in the front. And it says, I'm 89.8% certain that there's a stone sitting right here. And then it also detects the sky stones. And you can see the labels down here. And it says, I'm 89.8% confident that there is a sky stone in this box. And so it's kind of cool because, again, even though it hasn't seen maybe this target in this environment, it hasn't seen this target in this orientation, maybe it's slightly twisted, it's this way, it's that way, it will look at the pattern and say, I'm going to make a guess, but I think that is a stone, or I'm going to make a guess and I think that is a sky stone. And that's something unique and powerful about this machine learning technology. So how do we get an inference model? Well, when we talk about training a machine learning system, there are different approaches to train a system. There's one approach, and that's the approach that we used in the first Tech Challenge, and it's called supervised training. In supervised training, a human provides example data. So in the case of the first Tech Challenge, I'm going to provide TensorFlow with pictures of the game element. Let's say I wanted it to detect this phone. I would devise pictures of this phone, and I would say, in this photograph, there is exactly 2 of these phones in different locations, and here are the locations of the phone, and this is, the name of it. It's called a phone. And I provide that example data, and then the machine is going to take that, and it's going to make guesses, and then compare its guesses to the results provided by the humans, and then says, this guess wasn't so accurate. Let me try changing some parameters and trying to refine my guess. And it'll keep doing that until the guesses that the machine makes for the data sets are consistent with the human provided guesses or human provided results. And that's called supervised training. The humans know what they want the machine to look for, and then they provide data sets to reinforce and train the system to recognize that. And that's very useful. For example, with the first Tech Challenge, we know we want it to be able to detect this type of game element. We know we want it to be able to detect this type of game element. So we're going to feed it images or data so that it will learn what we think are these elements, and then it'll be able to make a guess of any image and say, I think in this image you have these elements based on the patterns that I'm seeing. Let's talk about unsupervised training. Unsupervised training is different. In this case, we don't know what we're looking for. So in this case, we are going to use algorithms that will allow our machine learning systems to look for patterns in data. So unlike the supervised training where we have a clear idea of what we want the system to learn how to recognize, in an unsupervised approach, you might be, for instance, trying to predict the stock market. You want to see what happens. Is there some financial data that I can look at to predict how the markets will behave tomorrow so I can make a lot of money? And in that case, you're using algorithms to look for patterns that you as a human might not be obvious. They might not be, spatial patterns. They might be, across multiple dimensions. And the idea is that you do unsupervised training on data to look for patterns and find relevance and find connections that you might not have seen before. And that's when you're training a machine and using unsupervised machine learning. And if you look at COVID, I was reading an article recently how they are doing that with the human genome. They're looking at people who have been sick and severely impacted by COVID, and then people who have not been sick and severely and not impacted by COVID. And they're trying to look at the human genome and see what genetic traits, are associated with or patterns or associated with people who get sick versus people who don't get sick? And can we make some predictions on how the disease operates in people so that we can better treat it? Okay, and then the last type of approach will be the training or reinforcement method. In reinforcement method, this is similar how you might teach yourself how to do something, or teach a pet, for instance, how to teach a dog to do tricks. You can use some type of reward system, and you develop an algorithm where the machine tries to optimize some kind of parameter or some kind of reward. And as it goes through, and makes a move or contemplates making a move, it'll calculate, well, how much of a reward will I get? And by trying to optimize or maximize or minimize some value, it can, maximize its reward. And that's a way for it to learn, how to accomplish the tasks. So all of these all of these approaches have different benefits. And depending on the type of application you're trying to solve, or a problem you're trying to solve, you'd pick an appropriate training approach to create your machine learning. And so for the first tech challenge, we use this supervised training, and our goal was to create a TensorFlow inference model, inference meaning educated guess, to detect the game elements in our seasons game. And then once we have this model, we will then want to convert it to a form that can be run on a mobile device like an Android phone, so that our teams can then use their Android devices to look for and detect objects in the game field. And in the past season, we were looking for either these yellow blocks, which were called stones, or these yellow blocks with these little special stickers on them, which were called sky stones. And to do that, we did supervised training. We used a convolutional neural network algorithm, and we created an inference model. And we started with a pre-trained model, and this is important. If you're gonna do model training, it's better, and I've been told this, and I'm not a machine learning expert, but I've been told by Google folks, and also from what I've read in the literature, it takes a lot of time to teach a machine to recognize objects from scratch. So it's always recommended, if possible, use a pre-trained model where it knows several objects and several shapes, and it's been already trained to detect these things, and then use that and provide additional data so that you can create your own custom model that's based on this pre-trained model. And for the first tech challenge, we used an open source model available from Google called MobileNet, and we specifically picked MobileNet because it provided us with accuracy, but it also was able to make these inferences quickly. If you look at this graph on the right-hand side, you can see on the vertical axis, we have accuracy. As you move up on this axis, the accuracy improves, so your ability to guess becomes better. But as you move along this horizontal axis, the amount of processing power that you need to make that inference or that guess goes up. So if you look over here, all the way in the upper right-hand corner, there's a model that's very accurate, but it takes a lot of processing power or a lot of computations to make that inference. And that's not necessarily good for a robot because you want to make these decisions quickly. So what we used was a MobileNet model, which gives us reasonable accuracy, but it's able to make these decisions at a quicker rate. And so we have a lower latency, and so that we're able to track more effectively these game elements using this inference model. And in order to do that, we had to create these training data sets, again, drawing the pictures, taking the training pictures and drawing bounding boxes around the objects we want to detect. And then we use those to generate a model using a supervised training process. It's an iterative process. The machine's going to guess and then compare its guesses to these training data sets that we provided, and then it'll iterate. It'll refine its guess and then check the answers again and do so until the error approaches zero. And we had to use a special system to do that because it took so much computational power to generate it. We actually had to run it on some special purpose Google hardware. Training data, we actually used for this past season 3,500 labeled images. And by labeled images, if you look over here, each image we had might have some objects. And in this case, we have 2 stones, which are the yellow blocks, and 2 sky stones. And we put them inside the image. They were inside the image and they were labeled. So if you see, there's a boundary box and a little letter S. And that means that this is a stone. And this boundary box is the location of the stone. Similarly, there's a boundary box here and a letter S indicating that this is a stone and it's located here. And then we had sky stones, which are represented by the T's over here. And what we did was we created these images so that the computer can use these to guess and check. It'll guess saying, hey, I think there's 2 stones here and 2 sky stones. And then it'll compare its boundary boxes with the ones that the human provided. And it's able to refine its guesses until its guesses are consistent with the human provided results. And we used a Google provided tool to make these annotated labeled images. And then we fed them into a supercomputer and we were able to generate our inference model. And because this was, pretty heavy duty math involved, we had to use something called a TensorFlow processor unit. And similar to a GPU on your computer that is optimized for graphical calculations, the TPUs are optimized for doing mathematical operations that are associated with TensorFlow. And we used 3,500 training images, and we took 12,000 training steps. And this process would have taken weeks or months on a desktop computer if it would even run at all, because the computer would run out of memory. But when we did it on this tensor processor unit cluster, it only took about an hour. And that's pretty cool. And by the way, this is available to the general public, and there are documents which I'll talk to later on about how you can do this and create your own custom model. So as we created our model, one thing that we were doing, how do you know your model's accurate? Well, we're measuring something called loss. And the idea of loss is when the computer makes a guess, it draws a boundary box around what it thinks is a stone, and then it compares it to what the human says was a stone. And ideally, they should overlap, and there should be very little error. And as that as that guess becomes more accurate, your loss value approaches 0. And what we did as we were training our model, we were monitoring this loss. And as the monitor value goes to 0, we can say, okay, as it's getting closer to 0, we understand that our model is becoming more accurate. And that's how we were able to tell that our model was getting better, because as the loss approached 0, we knew that it was making more accurate guesses for a variety of scenarios or a variety of test cases. Okay. Here's a quick video of the Skystone model. And what we see here is the output from a robot controller, and it's actually using this TensorFlow technology so that it can actually see these individual game elements. So on the left here, we have a sky stone, and on the right here, we have a stone. And again, this is using TensorFlow and the technology. And even if you were to twist this stone around and it's never seen it in that orientation before, the inference model will allow TensorFlow to say, hey, you know what? I think there's actually a stone, and it's right here in your field of view. And that's one of the powers of machine learning. It can make these guesses and find these objects, even though it's never seen that object in that particular environment before. Okay, so let's go down to the next slide. Okay, machine learning tools. I just wanted to cover quickly. This is pretty heavy duty stuff, and this is advanced stuff, but I just wanted to cover quickly what tools that we use specifically in case anybody out there is interested. And again, this is really heavy duty stuff. You really need to know a lot of Linux commands, and you need to know a little bit about software and a little bit about how to install these software packages to be able to do this. But if you're interested, you can use something called TensorFlow Object Detection API, and you can create your custom inference model, which is what we did. And that's how each season we're able to teach TensorFlow to recognize new things. And you could take the same technology, for instance, and teach it to recognize your dog, not anybody else's dog. You can teach it to recognize your dog. And when your dog is taught, and when your system's taught how to recognize your dog and nobody else's, you can, for example, write a program that whenever it sees the dog and it recognizes that that is your dog, it maybe turns a servo to feed your dog a treat. And that's what you can do with this TensorFlow Object Detection API. Now, it's heavy duty stuff, but if you're interested, there are online tutorials, and I like to use these ones from medium.com because these are written by Google engineers or people who work for TensorFlow. or work very closely with TensorFlow. And they'll teach you how to use the object detection API and how to install it. And then there's a specific tutorial that we use to teach us how to use this TensorFlow cluster or TPU cluster to do a custom model in a short amount of time. Okay. And so again, these I'm not going to go into too much detail because these are heavy duty, and you really do need to have some high-powered experience using Linux and some software packages. But if you want, it is an option, and you can learn how to create your own custom model using these tools. And in order to generate those annotated image, we actually use something from Google, a Google-provided tool. And if you were to go to this GitHub repository, you can actually download the tool and look at the instructions yourself. But this tool, and I'm going to share my screen if it's working, and I apologize because this is Linux. I'm running Linux over here. But you can use this tool. Let's see if it works here. I'm sorry, I shouldn't do a demo here. Okay, let's try this now. Okay, this tool provided by Google allows you to create these annotated images. So the way we did our images to train the TensorFlow system to recognize these game elements for the Rover Ruckus season was we took videos. So we took our cameras or smartphones and we took videos of these objects. Then we used this tool to allow us to draw boundary boxes around these objects and label them. And you can see that I have this gold box labeled with a G, and this other gold block labeled with a G, and then this silver ball labeled with an S. And once I've done that and I've labeled it, then I could use this tool to actually automatically start tracking these guys. And what it's doing is it's looking at my video and stepping through frame by frame, and it's drawing boxes around them and keeping track of these objects. And what it's doing is, and I'm going to pause it, it's generating all of those training frames that we're going to use to teach the robot how to identify these individual objects. And if I need to adjust it, like if the box is getting a little bit too small, or if it's getting a little bit too big, I can pause it and then, adjust these boxes. And then once I've adjusted the boxes to make sure I'm accurately, tracking these things, I can resume the tracking. And that's how FIRST was able to take a whole bunch of videos and then teach our robot or generate an inference model that would be able to detect these gold cubes and these silver balls. And the idea is that we use video and this tool, and we create a set of training frames or pictures that have this information on where these items are located. And then we can then feed this into the TensorFlow object detection API, and it's going to use that information to create an inference model. Let's go back here. And this is the workflow for doing that. We took the videos with the cameras of the objects that we wanted to detect. We used that Google provided tool to generate the labeled data to say, hey, these are the objects you want to track. These are the names of the objects, and then you go do that. And then we converted the data set into a format that TensorFlow could read. We uploaded these records into a Google Cloud server. Then we used the Google Object Detection API to train the model from a pre-trained model using those super powerful Google TPU machines. And once we were done, we converted it into a format that our Android phone could read. And then we installed it on our app and tested it. And again, that's pretty heavy duty stuff. And this is an example of the data set or the annotated data set. But it took a lot of work because it needed specialized knowledge on how to install and run these Linux packages. We're currently working with Google, however, to create a more user-friendly, what we're calling a machine learning toolchain. And the idea is that you can use your web browser, You can use your web browser to upload videos that you took of the objects that you want to teach your computer to recognize. And then you can use a web browser to create all of those annotated video frames. And then you can then use your web browser to kick off a supercomputer training run and generate your model that you can then use to detect your objects. And we're doing that with Google so that you won't need any advanced Linux or software skills to be able to do that. You'll just have to understand the process and have a web browser and an internet connection. And here's an example of the actual screenshots from this tool chain. What I did was I uploaded a video of these old blocks, which were prototypes from the Skystones season. And I used the Google tool with my web browser to draw these boxes around each of these objects. And each of these boxes have coordinates, which are listed over here in this table. And then I can add a label for each one of those objects. And after I've done that, I could push this button, and this Google tool will then, host it on the internet, start tracking and labeling all of the frames within this video. And when I'm done, I have a data set that I can then use to create a TensorFlow model that would be able to detect those little blocks in this field of view. And again, the whole purpose of this Google provided tool is to do all of that training, but not have to require any specific Linux knowledge or not have to understand how to install packages to troubleshoot them. It's if you have a web browser, you have some video footage, you can upload it to your cloud account, and then you can run this process through your web browser and create an inference model. And that's pretty cool. And that's something that we're working with Google on. We hope to pilot that technology in a very limited run next season, and then hopefully make it more generally available in a future season. Once you create your inference model, then you can use the First Tech Challenge software development kit and incorporate those models into your robot op mode. So you can use these models to detect objects and then write programs so that your robots can respond to things that it sees in its field of view. So again, going back to the dog example, if you train it to recognize your dog, you can have it feed your dog treats whenever it sees your dog's face. Okay, and that would be something that you could do with a custom inference model. Okay, I wanted to end up with fun activities to try and then just open it up for any questions and answers. But here's a fun one. It's called Google's Teachable Machine. This is not anything real difficult. It really is just, let me see if I have Teachable Machine queued up here. Okay, so I do have that. Okay, Google's Teachable Machine is a really user-friendly way for you to explore using machine learning. And it's a cloud-based system, and it lets you teach or create an inference model or teach the machine to recognize either images, sounds, or poses. So you can teach it to recognize sounds and words, like you could teach it to recognize hello and goodbye. And then once you have taught it and created this inference model, you can export that inference model and then use it perhaps in a Python program or in an Android app to do kind of cool things. And you can see, like in one case, it looks at a marshmallow and it looks at a not marshmallow. And if it's a marshmallow, it'll sort it to the right. And if it's not a marshmallow, it'll sort it to the left. And those are the kinds of things that you can do. And you don't have to go through this whole convoluted process, no pun intended, of using all these advanced tools or all these Linux kinds of things. You can just do that. Where is my presentation? You can just do that using the Google Teachable Machine. So again, Google Teachable Machine, friendly cloud-based application that lets you from your web browser teach a model to recognize an image, sounds, or poses. And if you see over here, that's me with my hands up. I taught it how to recognize 3 different poses. And once I have it taught to recognize the poses, I can then export these models and then use it in a Python script or use it in a Android app to do kind of cool things. So here's an example, a pose recognition example. I'll actually show you the demo, but what I did is I taught it to recognize 3 different states. The first state was up, and I used my web camera to take lots of pictures of me doing this with my hands up in the air. Okay, and that was my data set for the up position. Then I took a lot of pictures of me in the neutral position, just sitting here like that. Okay, and I did lots and lots of pictures of that, and then I used that as my data set or my supervised training set for the neutral position. And then I did the last step was the shoulders. And then I did that and I trained the model, and then the model can recognize my pose. Let's see if it works here. And if you look over here on the right-hand side, that's my face. And if you look over here on the bottom, this is what it thinks the output is, okay? And if I sit like this, it says, oh, he's probably in the neutral position. If he puts his hands on the shoulders like that, it says, oh, he's probably got his hands on his shoulders. If he puts his hands up like that, he says he's probably got his hands in the up pose. Okay, so this is just kind of a fun thing, right? And if I do this, I can then export this model by pushing this button. And now I have that model which I generated, which I taught it how to recognize these different poses. And then I could write an Android app. And maybe I write an Android app to play a sound when I do this. Maybe I write an Android app to turn on a motor when I do this. And maybe I write an Android app to turn off the motor when I do this. Okay? And that's the power of Teachable Machine. And it's something you can do with your web browser. You don't need anything fancy. And it's free. Okay? Let's move on, and we only have a few more minutes. The other thing I wanted to show you is there is an example on how to use TensorFlow Lite and a pre-trained model and use that to create an app that can recognize things. And what that does is this app is an Android project that you can download from this Google repository, and it has the MobileNet SSD model. And it'll automatically download it and import it for you. And you can create an app and see how it works so that it can detect a variety of common objects. And if you look in the screenshots here, I have on the left-hand side the TensorFlow sample app, and it's looking at a cell phone. It may never seen that cell phone or that type of cell phone before, but it looks at it and says, based on the pattern, I think that's a phone. And I'm 80.08% positive that that's a mobile phone or a cell phone. Similarly, it can look at something like a laptop, or it can look at a clock, or it can look at a cup. And it says, you know, I'm 80% certain that that's a laptop, or I'm 90% certain that's a cup. And that's kind of a fun application that you can do. And you could use a pre-trained model automatically. And if you get more sophisticated, you can actually create your own custom inference model and have it detect your own things. Maybe your dog's face, maybe, you know, something that wasn't detected by the previous model. And that's cool, and that's also available, again, from Google on this repository. And the last thing is, if you're interested, you can take a look at the online documentation for the First Tech Challenge control system, and you can learn how to use TensorFlow to detect objects using the First Tech Challenge software. Now, again, each season, the inference model provided with our software is different. This is showing the inference model for the Rover Ruckus season, where it was trained to detect those gold and silver elements. And this past season, it was the Skystone season. So the actual inference model was trained to detect those stones and sky stones from this past game. But again, these are all fun things that are available on the web. And if you're interested in getting a sample of machine learning, that is a good place to start. And with that, I'll open it up to questions. And I have a question for the host. Will these presentations be available online because they have the links embedded in them?
Yeah, I'm pretty sure these videos will be put up.
Okay, great. So you'll be able to find these, you know, kind of free tools available through these presentations online.
Okay, so we have some questions from the chat. So the first question is, what do you see as the future for AI and machine learning for FTC going forward?
As far as the future, I think there really is interest in trying to get kids to actually, for instance, generate their own machine learning models. So an idea is like in past First Tech Challenge games, you know, we had a team scoring element. The teams had to create a custom element. Some 3D printed it, some just built it out of wood, some built it out of paper. Whatever they make as the game element, I think there's a desire to be able to make a user-friendly tool that would allow teams to teach the computer to recognize that game element. And that way, during the autonomous portion, a robot could identify its custom, you know, game element and then manipulate it to score extra points. I think that would be an example of a fun way to incorporate the machine learning and artificial intelligence technology while still providing a fun competitive experience for the actual challenge. So.
Yeah, thank you. We also have another question from the chat. Do you have any tips on how to integrate machine learning into mentoring students on classical control system approaches?
That's a good question. I guess, yeah, I mean, the way I would approach that would be to, in essence, you can use machine learning sort of as a sensor. So in the case of the TensorFlow object detection API, you can, or TensorFlow object detection, the way it's set up for the first tech challenge control system, you can get, for instance, information about the objects that are detected and their relative location inside your field of view. And then you could teach a student how, for example, using sort of classic closed loop control, how you would navigate so that you get that object to be a relative position that you want it to be. So like if in Rover Ruckus, I think you had to move the gold cube out of the way, and we taught teams how to look for the gold cube, and then they would use sort of proportional control to line up the cube so it was in the center of its field of view. Then we had them learn how to scale it so that they can use proportional control so that they can move so that they're precise distance away from the element, and so they can manipulate it. So I think if you approach machine learning in that manner, you can combine it with the classical sort of control problems that you encounter in robotics. I hope that was the question that they were asking. So.
Yeah, that sounds like it would be really useful for mentors to use, so thank you.
Yeah, and the key thing is machine learning can be complicated, but in this way, the way it's presented through the first tech challenge, you can use it as a sensor. So if the kids understand conceptually how it works, but they don't have to know the details on how the model is generated or how the model is working, that would be a good way to incorporate it into such a lesson.
We have a few more questions from the chat as well.
Sure.
Which tool do you recommend for rookie or newbies teams to try and use for FTC Vision?
So I would look at, it depends. What I would look at for if you're an FTC team, I would first play with Teachable Machine just because it's fun. That is the Google Teachable Machine, over here. This is just kind of a fun thing, and that doesn't necessarily apply to a first tech challenge, but it's a fun way for them to learn about sort of machine learning and artificial intelligence. And as far as which kind of computer vision things, there are pretty good tutorials, for instance, like on this Vuforia technology. We talked about this Vuforia, and we have this demo where this robot is following stuff around. This is actually the proportional control. It's really just looking for this image, and then it's knowing where it is with respect to this image, and it's just trying to keep its position relative to that target, fixed. It's always trying to stay directly in front, about 9 inches. I would look at the tutorials on the First Tech Challenge website, maybe that talk about how to use TensorFlow and how to use Vuforia. So I think there's something here called using computer vision in FTC on this online forum. I'm sorry, on this online documentation as part of the First Tech Challenge GitHub repository. And if you look at computer vision overview, it talks about the different types of technologies and their advantages and where you might use one versus the other. And then it also actually has tutorials, and it tells you how to use Vuforia. Like if you wanted to use Vuforia to navigate on the fields, it has pretty explicit examples. And then it also talks about how you might use blocks. Use TensorFlow and how you might use that, for instance, with this past season's game. So I hope that helps. That if you're new to the image processing, that's something that you could do in the First Tech Challenge.
We also have another question. Someone was asking if they can use TF-Lite, if they can use a TF-Lite file from Teachable Machines with the current robot controller.
I'm not sure, because I think the robot controller is an object detection. It's expecting an object detection inference model, and the Teachable Machine is going to provide you with a either The image one, I don't know if the image is actually a classification. It might be a different model. It might be a classification model as opposed to, how do I do this? Wait, what am I doing? It might be a classification model as opposed to a object detection model. So I don't know if you could move that right into a first tech challenge op mode. What I would do is, if you wanted to do this, you can generate these inference models using Teachable Machine, and then you can either use a Python script and maybe something like a Jupyter Notebook to do image, sound, or pose recognition, or you can look online. There's probably some example Android apps that are not from FIRST, but perhaps from Google, which show you how to use these inference models. Yeah, but I think because these are different from the type of inference model that's used by the First Tech Challenge software, which is specifically an object detection model, I don't know if you can necessarily, go from one to the other.
Okay, cool, thank you. Another question. Another team was wondering if they can use more than one video camera to help the machine or the robot to learn.
Yeah, so if you're doing Teachable Machine, I think the user interface only lets you use one camera at a time. But if you're doing inference learning, you can, you're basically just taking videos and creating them. The Teachable Machine, though, only allows you to use one camera at a time, even though I think it detects all of the cameras that you have. Like if you look at my example, it was only using my laptop camera. So if I look over here, it's only using my laptop camera over here. But yeah, you can select the webcam. And for some reason on my Windows machine, it doesn't use this other camera. It just always defaults to the laptop camera. But yeah, I mean, in theory, you can use different cameras, and it does work on an Apple Macintosh system. As far as once you have your model generated in the First Tech Challenge control system, you can actually have more than one camera connected to your robot controller. And you can, I believe, switch between one camera versus the other and use one or the other to do your detections. So I don't recommend doing that because it is kind of resource intensive, but I think you can actually do that. Our software lets you do that.
Cool. And this might be the final question.
Okay.
Do you know of any FRC machine learning technologies? Like, can these same ones be implemented for FRC? Or
That's a great. And actually, so we demonstrated this to some folks within FRC and WPI, and they actually had some points, had a project to try and get machine learning available for FRC teams and trying to provide FRC teams with the ability to create custom inference models using AWS servers. But that was only a short trial for this past season. What I believe is possible is that you can use an Android controller with something called Coral, which is a TensorFlow accelerator, hardware accelerator. And I think the FRC rules allow you to use an Android device, and maybe it's not even Android. I think it could be a Raspberry Pi with this Google Coral device, and you can do machine learning on there. You can create an inference model using these tools that we talked about, and then you can load that inference model onto a Raspberry Pi. And if the Raspberry Pi is using Coral, I believe it can have an accelerated effect so that it can do the object detection at a pretty fast rate. And there were some tests done with WPI, Brad Miller over there at WPI, to try and implement some machine learning capabilities for FRC. And I think that would involve using a supplemental controller in addition to your RoboRio. And I think it's an Android-based or a Linux-based controller. I think it's actually Linux-based, and it uses a Google hardware product called Coral, which is, let's see, Google Coral. There's a USB accelerator which you can plug on, and it would allow you to do these TensorFlow calculations with hardware acceleration. So, yeah. And I think if you're interested, you could reach out through the group here and get in touch with me, and then I'll get you in touch with the people in FRC who have been doing this. and I think it's primarily Brad Miller of WPI. I hope he doesn't mind me mentioning his name, but he's in charge of also the WPI lib, which is the SDK for or the the programming API for the FRC control system.
Thank you very much for your presentation. It was very interesting. I definitely learned a lot, and I hope that the viewers did as well. So thank you for joining us tonight.
Thank you, everybody. Enjoy the rest of the 24 hours of STEM. Bye-bye.
Bye.